Oh my God, how do you follow that? Seriously. Wow. And furthermore, what a great conference. It's been so much fun to be here. It's so neat to see these, different verticals of places market design has had a big impact, and people, speaking kind of in a coherent way about each of those topics, and then to just be asked to talk about my entire discipline as the topic of my vertical. It was kind of daunting. So I decided to sort of subvert it and try to talk instead about the actual market design project that I've been part of, and try to think about how my disciplinary perspective impacted me. But I didn't recognize that the apparently boring sounding regulation panel before me would in fact be a bunch of really animated people talking about AI much more boldly than I'm going to. So I said here that if time permits, it'll be followed by ill-advised rampant speculation, but I set the bar for myself pretty high for ill-advised and rampant. So maybe not as rampant as I thought. But anyway, look, I want to begin by saying AI, actually, like as an AI researcher, it's sort of a frustrating thing because AI is a really ill-defined category. It's got a porous boundary between AI and the rest of computer science, operations research, data-driven parts of economics and statistics. And furthermore, there's this thing that some people call the AI paradox, which is that once we understand something, people no longer want to call it AI. Chess-playing programs don't feel like AI to us anymore. John McCarthy invented multitasking. That used to be considered an AI technique, but it's not anymore. I was talking to Hal in preparation for this talk, and he said I'm allowed to quote him on this. He said he distinguishes between AI and ML because he understands ML. And so if we've lost ML now, we're not even allowed to talk about that as AI, then we're really in trouble. And if the definition of AI has to be that it's something we don't understand, then I'm really screwed talking about this for half an hour. So I'll let you be the judge. But I'm going to take a narrower and more maybe boring perspective about AI. I think from the perspective of market design, I want to think about an AI approach, in the context of market design, as any approach that automatically gets better as we give it more compute and/or more data. And maybe that sounds like kind of a low bar, but a lot of what we do in market design doesn't really meet that bar, right? A lot of what we do in market design is pretty static in terms of the kinds of assumptions it makes and the sense in which those assumptions can be based on data, and it's pretty static in the way that it leverages compute. It sort of computes some function and then it's done. And so I want to think about ways that we can go a bit beyond that. And sorry, this is not a talk about ChatGPT. I really wanted to focus on things that actually got completed and had to do with the market. Although I'll speculate at the end. Lastly, the other caveat I want to give is that successful market design, and I think a theme that a lot of people have really been mentioning in different parts of this workshop, has been that successful market design needs simultaneous consideration of economic, computational, social constraints. And so I'm not going to talk only about the AI elements of a market, but I'm going to try to highlight as I go ways that AI made a difference. So overall, just trying to think about how AI can contribute to market design. It can be used to help overcome search friction problems when matching with an interested counterparty is hard to do. It can help people to express preferences, particularly when those preferences are complex or nonlinear. There's been a lot of focus throughout the time that I've been working in the field on designing algorithms to clear markets in the presence of these kinds of complex preferences. And then when big data becomes available, this opens the door to using machine learning in a variety of different ways. So we can use machine learning to give information to market participants. We can use it as an input to the market rules themselves. We can use it to optimize the performance of the algorithms that lie underneath the market. And we can use it to enable simulations to study how well markets worked. And I'm going to touch on a bunch of these themes in the case study that I want to talk about, which has to do with the FCC Incentive Auction. Many of my collaborators on this project are actually in the room. So Carla's here. I didn't work directly with Larry, but Larry's here. And of course, I'm being followed, as though following the regulation panel wasn't hard enough for me. After my panel, then the Nobel Prize winner who led my the thing that I was a small cog in the wheel of is going to speak after me and correct all the mistakes that I make. I want to call out specifically my student Neil Newman, who took the lead on many of the things that I'm going to talk about here. And basically, I want to say a little bit about how computation fed into the incentive auction in the first place, but then I'm going to focus a lot on how we can study it after the fact using kind of AI techniques. So kind of quickly to begin, because this is meant to be retrospective, the incentive auction began as an attempt to repurpose wireless spectrum from television broadcast to more profitable uses. And as an economist or an economically minded sort of person, you might wonder, why would we need a government to do this? Why can't we just allow trade to happen? And indeed, Coase, even writing in the context of telecommunications auctions, made this point that for an efficient allocation, all we need is clear property rights and no frictions. But unfortunately, there's a really critical friction in this setting that gave rise, that interacted pretty substantially with some of the computational issues, which is holdout power. So wireless companies need big contiguous blocks of spectrum in order to be able to make profitable use of it. And individual channels could threaten to block entire transactions for big payouts. And so any efficient market would then have to enforce really high payments to each channel, wouldn't budget balance, and the whole thing wouldn't work out. And so the people who designed this auction made a really clever definition of the property right underlying the market. They really let everything get off the ground. And I guess that's been another theme of this workshop, that defining the property rights, the goods, properly can really make a big difference to the market design, rather than taking these things as given. So here, the redefinition was that stations didn't necessarily own the actual frequency that they were broadcasting on. They owned the right to broadcast without facing substantial interference. And this made stations into substitutes for each other, fostered competition, made it possible to clear a market. Another question that the FCC faced was how much spectrum to clear. It was not clear how much interest there would be for buying this cleared spectrum, and they didn't want to buy back a whole bunch of spectrum from TV stations and then discovered that they couldn't sell it. So they came up with a bunch of different band plans for what they might do if they cleared different amounts of spectrum. Given that there's in the standard economics case, you try to make supply meet demand, but here there's no homogeneous good. There's no single price across the entire country, and so this was a tricky question to think about. And another kind of key economic market design principle is to try to define property rights in a way that makes you not have an externality about who else gets allocated. So you shouldn't have to care who wins and who doesn't win. In the incentive auction, this meant that you shouldn't be interfered with other people who remained on the air if you yourself remained on the air. So when we changed the channel that a given station was broadcasting at, it was important that it not cause more than minimal interference to any other channel. Unfortunately, though, this was a computational non-starter to do exactly. So quantifying the number of customers affected by interference on a given assignment of channels to all of the stations, there's a piece of software the FCC had that they could use to figure this out. It took days of computer time, and with almost 3,000 stations being packed into 29 channels, there were 10 to the 4,300 possible assignments, each of which would have needed this much computation to do. So this just couldn't be done exactly. And so here came another really valuable redefinition that got this problem off the ground. A ruling was made that a station would be considered to suffer minimal interference if no other single station interfered with more than 0.5% of its pre-auction audience, rather than in the aggregate across all of the interference that it received. And that allowed these pairwise constraints to be pre-computed. Even so, even with this simplification and thinking in terms of pairwise constraints, the problem of determining whether there existed any channel assignment for a set of stations is an NP-complete problem. It's a graph coloring problem. And so the worst case running time of solving that problem is going to have to scale exponentially unless P equals NP. And so this kind of gives a second response to the sort of Coasian argument about why shouldn't you just allow the market to take care of all of this, because this would imply that the market itself can solve arbitrary NP-complete problems to reason about this kind of thing. So the ultimate clock auction design that the FCC put in place had an ascending price auction for telecoms, where they sold spectrum that would be cleared. They had a reverse auction where they bought spectrum, and when the two auctions terminated, they ensured that the amount of money that they collected was greater than or equal to the amount of money that they had to spend in buying the spectrum. And if that didn't work, then they reduced the clearing target and started again. That's how they solved this problem of deciding how much spectrum to clear. So I got involved in the feasibility testing part of this project, which asked this NP-complete problem of whether a station could be accommodated on air if they no longer wanted to participate in the auction. So the way that the reverse auction worked is stations were given a price offer. Somebody would come to you and say, will you sell your station for $10 million? And you'd say, yeah, that's an easy yes. I definitely would sell my station to you for $10 million. And then, in the next round of the auction, they'd say, well, sorry about that. How about $3 million? And you'd say, well, not quite so easy, but sure. And then, they come back to you and say, what about, $800,000? And you'd say, no can do. I'm going to go back to being a broadcaster. And at that point, there had better be some spectrum to put you in, right? It better be possible that there's actually, interference-free channel that you could be put on that would make the whole auction feasible. And so each price movement in the auction needed to be backed by this kind of proof of feasibility. It didn't actually mean that really was the channel that we assigned people to. That was Carla's problem to figure out later. But this just was a certificate of feasibility. And this was a tough graph coloring problem. And there was initial skepticism about whether we could, in the runtime of the auction, solve this exactly at a national scale. This was the actual constraint graph of the auction. But there was a really beautiful element of the auction design that I want to highlight, where if we couldn't solve an instance, then we would just treat the unsolved problems as being infeasible. So if we timed out, then we would say, well, this problem, maybe is repackable, but we're just going to treat it as being not repackable, which means we don't lower the price for that station. And that maybe costs us a bit of money, but it doesn't break the whole auction. And so I really like this kind of paradigm of a market design that relies on a hard optimization problem, which we do our very best to solve. But if it doesn't work out, then we can just lean on a little bit of a degradation in the economic quality of the outcome and have this really nice trade-off there. So that's something I'd like to see in more markets kind of going forward. So we took the bit between our teeth and we built a feasibility checker using all kinds of different AI techniques to try to make it as efficient as possible. So we encoded the problem as a satisfiability problem. We took a wide range of open source SAT solvers. We used a technique called algorithm configuration, which you can think of as being machine learning in the space of algorithm design, where we say, I have a sort of hypothesis space of parameterized algorithms, and I have a distribution of problems I want to do well on. I want to minimize the loss in that space, which is find an algorithm parameterization that performs well on this distribution of problems. We also combined this with an algorithm portfolio technique that says, I want not just one algorithm, but a whole bunch of algorithms with uncorrelated performance. I run them in parallel. I only care about whichever one of them finishes first. And we had a bunch of other custom optimizations. So we kind of threw all kinds of different kind of algorithm design AI techniques at this. And we eventually built something that was really fast and much faster than the techniques we had before. And the auction happened, and it happened once. And a bunch of spectrum changed hands and a bunch of money changed hands, and that's it. So then we got interested in trying to ask, was the incentive auction design a good design? Not just did it work out well this one time, but how would we think about whether this is a good design? And here's another sense in which I want to use really extensive computation to try to ask an economic question. And so I would consider this a AI technique. So we conducted really extensive simulations where we built an auction simulator that, as far as we know, is the highest fidelity simulator of this auction that takes sometimes days to run an individual simulation. We constructed a bidder model with parameters describing bidder valuations and bidder behavior in the auction. It's too much detail to go into here. We establish a probability distribution over all of these parameters, and then we draw many samples from this distribution to get different possible bidder behaviors that we might have in an auction. And then we run paired simulations, holding the valuations fixed and varying some facet of the auction design. And then we can look at what kind of difference it made, and we can compare outcomes both in terms of cost and in terms of value loss. So how much reduction in efficiency there was by reducing the number of broadcasters on the air. The hope would be you would buy out the low value broadcasters and keep the high value ones on the air. In this vein, I can now say, in terms of our feasibility checker, not just was it fast when we ran it, but did it actually make a difference to the economic outcomes of the auction? And so here are some CDFs of various different feasibility checkers that people used. It doesn't really matter if you can read it, which of course you can't. But what I want to say here is that within our cutoff time, which is the right side here, the fraction of instances that each solver was able to solve, and the ones at the bottom, Cplex and Garobi, are solving sort of 20%, 30% of the instances. Some of the existing SAT solvers are solving sort of 60%, 80%, and then we were solving like 98% of the instances. But did that matter? So for these experiments, I'll walk you through the setup a little bit more, and then I'll show you some other things more quickly, just showing you how we do this. So we simulated, in this case, UHF only national spectrum auctions, an 84 megahertz clearing target. We gave the feasibility checkers 60 seconds, and we took a valuation model from the literature that I'll call MCS for the maximum of cash flow and stick value. Don't worry if you don't know what that is. And we took 50 valuation samples from our model, and we varied only the feasibility checker on each of those paired samples, and we looked at what happened. And then, of course, there's some variation just because sometimes people with high values will pay you more than people with low values. And so we normalized by the cost and value loss that we got with SATFC, our own feasibility checker. And we looked at how much proportionally better or worse we were on each sample for the other feasibility checkers. So I'll have a graph here, a scatter plot, where every point in the scatter plot represents two simulations, one of SATFC that was used to normalize, and one of the other feasibility checker that we ran through an entire run of the spectrum auction that involved solving tens of thousands of feasibility checks and doing the entire trajectory and then seeing what happened in the end. So the graph on this slide took about half a year of computer time to generate. And this is actually the smallest, you can follow along with those numbers throughout the talk. This is the smallest amount of CPU time of any of my graphs. And so the scatter plots on the x-axis, I'll show you the normalized value loss. So less loss is better. That's normalized cost on the x-axis. How much did the FCC in our simulation have to pay to clear the spectrum? And here's what we found. So the red diamond for SATFC in the bottom left-hand corner, of course, is at 1 because I'm dividing it by itself. So all of the SATFC runs are going to be in the bottom left-hand corner. That's a sanity check for you. But when you do empirical work, you don't normally see something this nice, right? So incredibly clean trade-off where we were improving both in value loss and in cost as the solvers got more and more effective. Really quite, and the proportions are quite big. So you see like a factor of 2 in cost. If we'd used Cplex out of the box, we would have paid something like 3 times as much in cost and lost about 3 times as much value. And the SAT solvers were better, but really big effects here. Now that was only one value model, and that was UHF only. So we can do this also. We fit another value model to the actual bid data that was returned by the FCC. Now we have only one sample, so we had to do a bunch of complicated statistics I won't get into. And we also can simulate the VHF packing that the auctions did. And then I can get graphs for all of these different scenarios. I'm not going to walk you through all of them, but you see the same pattern occurring where we get nothing. We have no simulations where we have fractions less than 1, which we of course could have had if something else was better. And we still see significant gains both in cost and in value loss. So this really backed up for us that making these algorithmic improvements can make a really fundamental economic impact. But we wanted to ask questions about things besides the feasibility checker. So here's another question we asked. I mentioned that the auction repacked the VHF bands as well as the UHF bands. So they only wanted to clear UHF spectrum, but the way it worked was if you were a UHF station, you could be paid a lesser amount to move to VHF, which is a lower quality way to broadcast, but you would still be a broadcaster. And then maybe you would displace some VHF station who wants to go off the air, who would have a lower value than you. So this could, in principle, lead to gains in efficiency and also in cost. But it made the rules really complicated. It was no longer obviously strategy proof, and it was hard to think about strategically, and it wasn't clear that there was enough value in the VHF band that this would be worth it. So we wanted to investigate whether this extra complexity helped, and looking at these simulation plots here, you can see that it looks like it really did in our simulations pretty robustly. So here I'm normalizing by the with VHF case, and every one of the blue dots is a normalized paired sample in the without VHF case, looking at what would have happened to exactly the same stations with the same valuations if we ran the same auction without giving them the opportunity to pack into VHF. And you see it almost always cost more, and it usually experienced more value loss. The star in these graphs represents the mean of all of the samples. So we do see a bunch of variation here, but still looks like this was a good idea for the FCC to have done. So way to go, Ilya Segal. Here's another contentious element of the auction that got a lot of discussion at the time. It turns out the prices didn't fall uniformly for all the stations. There was scoring that basically increased the prices for the initial prices for stations that caused a lot of interference constraints, and also there was a scoring based on population that sort of was a kind of Meyerson pricing sort of thing that would offer lower prices to stations that looked like they would most likely be willing to accept lower prices. The latter was especially contentious. There were actually protesters in front of the FCC carrying these signs. And particularly because this was contentious, we wondered whether it was a good idea. So here we sampled auctions. We ran them in 4 different scoring systems. So we looked at what if we scored based on not at all, based only on interference, based only on population, or based on both, the way the FCC did it. And here we got a really muddled message. Our simulations don't really give much evidence that scoring helped either in terms of cost or in terms of efficiency. So there's one case in the MCS model in the VHF plus UHF case, there's a decent trend, but in the other cases, it's really just a cloud of points around the center. So this really didn't, this looks like a case where in retrospect, this might not have been worth the political cost. Yeah, the guy with the sign. Well, I mean, it didn't make anything worse either, but the last question I want to talk about was this question about how many channels to clear. So the FCC let market forces determine how many channels to clear by doing these alternating rounds between the forward auction and the reverse auction. And this wasn't an element of the design that received, as far as I'm aware, a lot of comment in the lead up to the auction. But we wondered how this compared to just clearing the right number of channels. If you had just known where the auction was going to end up and just cleared that number of channels. So we ran a 4-stage simulation mirroring the real auction. And we compared it to a single-stage simulation that just cleared the last round, again, pairing all of our samples. And to our surprise, we found that this was reasonably bad. So it pretty consistently increased costs and reduced value compared to not having done this multi-step thing. So, and the problem was that we would sort of drive a hard bargain in the reverse auction. We would sort of force in some commitments, as we kept grinding the reverse auction down, and then we sort of made this greedy commitment that we didn't undo later. And this led us to wonder, what if instead, this is something that, as far as I know, wasn't proposed when the auction was being considered, but this led us to wonder about it. What if we'd run the forward auction first? We'd known what the forward auction revenue target was. And then when we ran the reverse auction, we just stopped it as soon as we hit that revenue target. Once we knew we weren't going to reach that revenue target, rather than running it all the way to completion, as was done. So we simulated that as well. By the way, look at the CPU years. The last one was 31 years, and this one was 50. And so this was a real beast of an experiment to run, which is why we did UHF only. But here we got pretty similar outcomes to perfect forecasting. So this pretty substantially mitigated those problems from running the reverse auction longer. I think if anyone wanted to use this design again, this is a change that I would seriously consider making. And so more broadly, I just want to argue for this kind of really extensive simulation backed by really careful statistics as a way of asking economic questions about a system that you can't just gather lots and lots of data about. Okay, so that's what I had to say about the kind of AI that we actually did. But I imagine you're sitting there thinking, yeah, okay, fine, you can call that AI if you really want to, Leyton-Brown. But tell me about the sexy kinds of AI that I read about in the newspaper. Here I think the fundamental catch in market design is to do with counterfactuals. So, machine learning is fundamentally about finding patterns in IID samples, and market design is fundamentally about optimizing over possible worlds and trying to find a possible world, that does well under some objective function. And most of these possible worlds are ones we don't have any data about because we haven't gone off and used them for something. And so this at least for this kind of, sort of pen and paper sort of market design, where you go off and study something for 3 years and run an auction and it happens once, it's pretty hard to see how ChatGPT is going to be the silver bullet that solves your problem there. That being said, here are some ways that I do think that AI can be impactful in market design going forward, even the sexy kinds. So one is to find clever ways of putting ML components into a larger system. Something I've got a passion for that others are working on too is building behavioral game theory models from data. So trying to understand how people reason in novel strategic situations by seeing examples of them reasoning in previous situations. And the behavioral game theory literature tends to fit very, very low parameter models to data, and in some cases not even really to think about fitting them to data. And but the machine learning person would say, this is a machine learning problem. I want to find something that if all I want is a predictive model, I don't necessarily need these parameters to be interpretable. Some other ideas are to leverage the natural language powers of systems like ChatGPT to do preference elicitation via natural language, or to build automated negotiation kinds of systems that would leverage the language abilities of LLMs. And fundamentally, I think we're going to start to see large language models used not so much as a replacement for other parts of the system, but as an interface into the system. So I think we're going to have messy markets with complex preferences, things like eBay. You sort of think of it as a giant mess of different sites that you can't quite understand. And you could see a language model as a way of aggregating all of that textual data and surfacing to you things that you might care about, and then you might give it some feedback about what you care about and might iterate. I should say, by the way, I had other challenges of that. I didn't mention it. I should say what I meant. One is a large language model. It does a constant time computation, right? It does one forward pass to predict the next token, and it can do wonderful things, and that can be a pretty substantial computation. But it's not going to solve the problem of computational complexity, right? It's not going to solve an NP-complete optimization problem in one forward pass. So this is another sense in which we have to be realistic about large language models. And not only that, but as you might know, GPT-4 is great at multiplying 1- and 2-digit numbers, but if you ask it to multiply like 4-digit numbers, it just makes stuff up, right? Because It just, and there, so we haven't, built a system that's, able to replicate a calculator because it's not trying to. It's just trying to, think about, words that chain together. And so I think we're going to see, in order for these systems to work in economic context, I think math is going to be pretty important. And so I think we're going to have to, reasonable people might disagree, but so I think we're going to have to build these systems in a modular way where they can call out to, we already see ChatGPT being integrated with Wolfram Alpha, but we're going to see, integration with optimization engines, integration with, other, economic subroutines. It's not like this thing is just going to hallucinate answers to economic questions. A second thing we can do, of course, is to learn models that explicitly reason about counterfactuals. And of course, I don't need to tell this crowd that causal inference is a big hot area. I mean, Susan, already said all the stuff about AI, so I get to now talk about causal inference, I guess. But we can go beyond that. So I think we're going to start seeing people using deep reinforcement learning as an agent model when we build simulations. So I think we can ask a simulation question. A weakness in our simulations is we need to specify how bidders will behave. And in the incentive auction, that was okay because it was obviously dominant strategies. But in more complicated markets, that's a big problem for simulations. And reinforcement learning offers a way to do something really interesting there. So I think that's a way that AI is going to change economic analysis. And I think we're also going to see large language models as a cheap proxy for human subject experiments, where you can just give different kinds of treatments to a large language model, sort of say, this was trained on a lot of regular people on the internet writing text. It sort of is some kind of a proxy for a regular person. Might not be exact, but on the other hand, you don't need to get ERB approval yet for what you do with GPT. So, if you want to, rerun the Milgram experiment in the comfort of your own home and, only inconvenience electrons, this is a way you can try to do it. Finally, it's something that I think the previous panel already touched on to some extent. I think we're going to see a lot of market design, not so much enabled by AI, but for AI. I think there are a lot of market design questions around AI. I think there's a lot of interest in how we should monetize LLMs. I think we're going to see, as search is ChatGPT answering a question for you rather than you going to a web page. This changes the way we advertise. So I think we're going to see product placement kinds of strategies or sponsored recommendations. And the technology exists on how to do this, but the way we would set up the market is really fascinating to think about, particularly given that LLMs are so unreliable and that they can sometimes do really unpredictable things. I think we're going to have to think about strategic manipulation of LLMs. So if you have sponsored recommendations, think about non-sponsored recommendations, right? What if I just put up a bunch of text on the internet that tries to influence LLMs that get trained on that text in order to recommend, my products in inappropriate circumstances? So I think we're going to see that kind of an arms race. There's going to be a question about how we price LLM access, particularly given that they're one of the most expensive consumer things that has ever been served on the internet, and also because there's this price quality trade-off, right? For a lot of things, GPT-2 is just fine, and it's way cheaper to serve. And so thinking about that trade-off is going to be interesting. And then we're going to see custom or fine-tuned large language models embedded in a lot of more complex services, and thinking about how to set up those partnerships, I think is going to be another really fascinating market design question. So I'm going to leave it there, and thanks very much for your attention.